This one is a little bit tricky. However, you can solve this problem if you want by taking this polynomial, finding its first derivative, plugging in 0. Then take its derivative again, plug in 0, and that will work perfectly fine. I want to warn you, however, that I've seen problems that ask for, like, say, the 21st derivative at the center. And you are not going to be taking the derivative 21 times. So you want to know where to find the function's derivative values at the center for any order derivative. And I want to point out to you that the f of x formula they're giving you does not look like the Taylor formula. But if you look at the terms that are here, if this is a function representing f, then this formula must hold true for every single one of the terms along the way. If you need to know the first derivative at 0, I want you to notice that that's going to happen when the n of the Taylor-Maclaurin formula is 1. Now, that's not going to happen for this formula at its n equals 1. At its n equals 1, it's giving you a second derivative formula, because when its n is equal to 1, it's creating an x squared term. So there are two different formulas really that are going on here. They're both the same thing, they're just written differently. And here is where you always want to look. If you want the first derivative, you're going to find it where x has exponent 1. If you want to find the second derivative at the center, you're going to find it where you see exponent 2, because based on the Taylor-Maclaurin formula, you're going to get second derivative when the exponent is 2. And so this continues on and on with any derivative order of the function at the center. But something also to be aware of. You only know values of these derivatives at the center. You only know at the center. If they asked you to find the first derivative at 0.5, they messed up the question if the center of the polynomial is 0. They would have had to say approximate f prime of 0.5. But they cannot ask you to find any derivatives of x coordinates that are not the center. Those are only approximations ever. And you need to be aware of that. So now, what I'm going to point out to you is, if you look at the polynomial as they gave it to you, written out one term at a time, you have a constant, but then it immediately goes to x squared, and it skips x to the 1 power. If a function, or if a power series is representing a function, then it must follow the rules of the Taylor-Maclaurin formula. The only way for the exponent 1 to not be a term is for the coefficient of x to the 1 to be, and you say the coefficient must be, I guess you're just not typing quickly. You don't have an x to the 1 term. Whenever you write a polynomial, if a certain degreed term is missing, you understand its coefficient to be 0. The only way for the Taylor or Maclaurin formula to give you 0 for a coefficient is if that particular order of derivative itself is 0. It's very important that you're able to read this polynomial and recognize that if you do not have x to the 1 power, that immediately answers that the first derivative at the center must be equal to 0 right away. You do not even need to explain yourself. In fact, if you have to explain yourself, it kind of shows that you aren't looking where you need to look. You're going to get so familiar with this formula and with looking at the polynomials it creates that you're going to reach a point where you realize missing terms mean for that particular exponent, that 6 shows up, but who doesn't show up? 5. X to the 5th doesn't show up. X cubed doesn't show up. All of the odd exponents don't show up. That means that the odd ordered derivatives at the center are all 0. Take a look also at the formula right there where I highlighted and realize that that formula is causing there to be no odd exponent terms. The n values that I plug in here. No, stop calling me unknown private number. When I use this n and I plug it into all my n's, n equals 0 is giving me my constant. But when I use n equals 1, that's actually giving me my degree 2 term. N equals 2 is giving my degree 4 term. And those n's are different from these n's. The Taylor series goes through every single one. So this n equals 1 is going to give you 0x. This n equals 2 is going to give you negative x squared over 3 factorial, even though this particular sigma formula is getting that from a different n. This will take getting used to. Don't panic. We're going to go over this enough where you're going to look at this later and you're going to be like, I get it now. Yay! I promise you, you're going to get there. Anyone who actually feels like they're getting it really easily right now, you're abnormal. In a good way. Abnormal is often a very good thing. Anyway. Now, to start again, f prime of 0 must equal 0 because there is no x to the 1 term. And negative x squared over 3 factorial must be equal to the Taylor formula's term that creates the second derivative at the center divided by 2 factorial times x squared. You can use this polynomial, take its first derivative all the way, take its second derivative all the way, plug in 0, and get an answer for the second derivative at 0. But I'm going to repeat and say that I have seen the AP test ask you to find, say, maybe the 5th derivative at 0, even the 21st derivative at 0, if the pattern is good enough. So you need to know how to find it within the polynomial terms. And what I do is I look at the coefficient. The coefficient of the given polynomial for x squared is negative 1 over 3 factorial. The coefficient formula for x squared is the second derivative of 0 over 2 factorial. So I'm essentially just getting the x squareds and canceling them out. So what does this mean is the answer to the second derivative at 0? Negative 1/3. So the first part of this problem is to find f prime of 0 and f double prime of 0, and this isn't the only way you can do it, but you need to know how to do it this way because that will take care of any time this situation shows up. Then we move on to the next question. The next question says, determine whether f has a local maximum, local minimum, or neither at x equals 0. I want to remind you that the center of the polynomial is 0, so you do know for x equals 0 what each derivative order is. I want to tell you that the first derivative test will not work here, but the second derivative test will. When you use the second derivative test, you're looking at, is the first derivative equal to 0? Yes. What is the sign of the second derivative for that same number? It is negative. Negative second derivative means concave down. Where is my slope 0 while I am concave down? My slope while I am concave down is only equal to 0 when I'm sitting up at that relative maximum. Therefore, this, come on, write for me here. This is the justification that you need to explain that f has a relative maximum. At x equals 0. Make sure that you state that inequality. And I'm going to warn you that it's very common for infinite series. Well, I should say this. If they ask you whether you have a local minimum or maximum, and you're dealing with an infinite series, most likely you're going to use the second derivative test, not the first derivative test. And then I want to also point out one other thing, because somebody in the last class asked me this question, and I think it's very, very valuable. if the first derivative is at whatever x coordinate, if it was not 0, so this is not this problem, not this problem. I am writing it to make sure you understand this is made up. If you found out that the first derivative at 0 was equal to, let's say, 5, what would be your answer to, is there a local minimum, maximum, or neither at x equals 0? And then I want you to think about why. What would be your justification? Because the derivative is not 0. If the derivative is not 0 and it is defined, then it is not a critical number. If a function does not have a critical number at a particular x coordinate, f cannot have a relative minimum or a relative maximum.